Here's some of the scalar surface integral and surface area problems that get pretty tricky. They get pretty involved, so I wanted to do a few of those, work them out. Number 41 was the area of the part of the surface z equals xy lying within the cylinder x squared plus y squared equals 1. Well, that is a saddle surface, and that's one of our classic saddles. This tells us that eventually we're going to be using polar, and I'll show you there's a couple of ways to set that up. One way is, we can go ahead and use the graph parametrization first. Because it's z is a function of x and y, we could always just use x and y as the parameters, and then just z equals xy. So that's one parametrization, and I'll actually show you the problem doing it that way, because it's just as simple as anything. Or we could switch to polar right away and do everything all at once in terms of r and theta. That's cleaner, but the algebra maybe is sort of introducing the sines and cosines slightly earlier than we absolutely need. The advantage of doing this version is, for example, if we wanted to look at this on the applet that we have, we'd like to tell the applet exactly to give exactly the surface we want with the right domain. And the way the applet works is it only uses a rectangle, like s from 0 to 1, t from 0 to 2 pi, as its domain. And so if you want to get just the surface you want and nothing else, we actually kind of have to go to polar right away. And of course here it's s and t instead of r and theta. But I've put it in as s cosine t, s sine t, and then of course xy turns into s squared cosine t sine t. Just like here, xy turns into r squared sine theta cosine theta. So let me show you, I did an example rather like this in class where we did actually go to polar right away. But what if we use the graph parametrization, just using x and y? The nice thing about that is there's a predefined special formula for that. It's in the book, that when you actually look at all the RU cross RV stuff, it does simplify substantially. And it turns out to give you this Jacobian factor, the square root of 1 plus fx squared plus fy squared. And of course fx is y and fy is x here, so you get this integral. And then it makes sense to change to polar. So that's going to be integral from 0 to 1 in r, or let's say 0 to 2 pi. We usually do the theta second, it doesn't matter here. 0 to 1, and then that's going to be the root of 1 plus r squared. And then, now, this is a dx dy, and so you really do need to put in, you are changing variables between Cartesian and polar in the ordinary way. This Jacobian factor was a kind of a Jacobian between the xy plane with x and y as the coordinates and this saddle surface. It has not included the r Jacobian factor yet. So when I talk about how you don't need to include that artificially, that's if you are going all the way directly using this kind of parametrization, all the way directly from x to r and theta. If you did that, you would get this whole thing, root 1 plus r squared times r, automatically in one fell swoop. Here we're doing it in 2 stages, but it actually does turn out to be a little simpler here, because it's kind of reducing it to 2 pre-done calculations, the graph parametrization formula and the polar Jacobian. Okay, and that's not too hard because you can do a u sub where u equals 1 plus r squared. Okay, so that's going to be one of the examples. Another one is actually rather similar. That's number 43. Another saddle surface, but now it's z equals x squared minus y squared. Of course, that's just a rotate of the y squared minus x squared. Sorry, that's just a rotated version of z equals xy, so it really should be very, very similar. And it's between the cylinders of radius 1 and radius 2. Oops. So that's x squared plus y squared equals 4. Okay, so we could do the same way. Or we could go ahead, let's just, to be different, let's go ahead and see how it works when we do all the way to, actually no, let's use the graph parametrization, because there's just an issue of like writing cross products on this computer program that would just be a little too slow. So the graph parametrization is going to be x equals x, y equals y, and z equals y squared minus x squared. Okay, and so we're going to get this exact formula almost, except we're not the disk anymore. Oh, shush, yeah, I know. I have to copy it in piece by piece. Wish it were smart enough to understand what I want to do. Okay. And now that's not going to be the disk, that's going to be the annulus, where r is between 1 and 2. But we'll put that in a minute. Okay, so now we're just going to take this and put in, now fx is minus 2x, and then that's going to be squared. So that's actually going to be a 4x squared. I misspoke. This isn't quite a rotation of xy. It's a rotation of 2xy. And so we actually get a factor of 2 and then squared is 4. And then fy is 2y squared is 4y squared. Okay. And now again, we just go ahead and change to polar. So for these particular examples, it is probably easier to do it without the crosses. It's great practice to do the cross products. Let me just do. But here it is actually a little simpler. So now the integral's from 1 to 2, because it's this between these two cylinders. And that's going to be 4 r squared. And that's going to be r dr. I went past it. D theta. And that's not a super hard integral. It's a very similar integral to the one before. Let's actually go ahead and look at the picture for that. That is going to be, now here, to parameterize it though, to get a good picture, we're going to have to go all the way to polar. So that's still going to be s cosine t, s sine t. Now that's going to be y squared is s squared. You know, they both have an s squared in them, so this will be a common factor. And then sine, times sine of t, and then squared, I think that works, minus cosine of t, and then squared. Now we will know what this should look like. Okay, I got to enter everywhere. And then s is the r coordinate. That should go from 1, enter, to 2, enter. Remember with this applet you have to enter in everything to make sure it actually updates. Whoa, okay, let's zoom out. Okay. And then rotate. Yeah, there's a saddle. It's getting pretty steep because we're going out where the partial derivatives are getting a little bigger. So it's a saddle, part of a saddle that's over an annulus. If you look at it from the top, it just looks like the annulus, but then clearly it's going to be a lot bigger than just the annulus. The annulus is very easy to calculate the area of. It's just pi big R squared minus pi little r squared. But we expect to get a substantially bigger answer because this guy is stretched quite a bit. Remember I talked in class about how the factor in the ds is a stretching factor, like a shadow factor. Every little bit of area on this surface corresponds to a much smaller bit of area if you project it down, which is what the graph parametrization does. Okay, well, that's a good place to stop for these, and I think I'll do another video with some different problems too.